Let's try a couple examples. So first, we limit as x approaches 0 of cosine x minus cosine 2x all over 1 minus cosine x. Now when you plug in 0 into this expression, it gives you 1 minus 1 over 1 minus 1, 0 over 0. This means we are allowed to use L'Hopital's rule. It might be possible to find this limit without using L'Hopital's rule, but even if it was possible, it would be a ton of work, much easier just to use L'Hopital's rule. Whenever I use L'Hopital's rule, for some reason I always draw an arrow and put an H on top. I think it's how the professor who taught me did it, and so now I've been doing it for like 20 years since. So, we differentiate the numerator, which is negative sine x minus 2 sine, plus 2 sine 2x over sine x. I apologize for that bad handwriting. One more note though, it is good to let the person who is reading your work know that you're using L'Hopital's rule. It's kind of good form to show that it's one of the two forms and then somehow give an indication that I'm using L'Hopital's rule, just so that the person who is trying to go over your work can follow your logic. So we differentiated. We now plug 0 into that. This gives us 0 plus 0 over 0. So we could do L'Hopital's rule again. We could also use a trig identity to rewrite sine 2x and then cancel out all the signs. That would work. But let's use L'Hopital's rule, because it's probably easier. Negative sine differentiates to negative cosine. 2 sine 2x goes to 4 cosine 2x over cosine x. And now we're good to go. Because when you plug 0 into cosine x, it gives you 1. So we know for a fact it's not going to give us an indeterminate form. Plug 0 to the top, it gives you negative 1 plus 4. We call that 3. And there's your answer. As another example, let's do the limits as x approaches infinity of log 3x over the 10th root of x. So we plug infinity into this. Both of these functions are slow growing functions, but they both go to infinity as x goes to infinity. So it's infinity over infinity. This is the other form, which we are allowed to use L'Hopital's rule on. So we differentiate the numerator after we give an indication of what rule we're using. Log of 3x differentiates to 3 over 3x. Derivative of the inside function over the inside function. The 10th root of x differentiates to 1/10 x to the negative 9/10. We then do some algebra to this. We don't want to plug infinity into this yet, because this is clearly not the best form to work with. So if you get a form that's kind of messy, it's smart to do your algebra to it first. Like 3 over 3x is 1 over x. This expression is the same as 1 over 10 x to the 9/10. When you divide by a fraction, you multiply by its reciprocal, so that's 1 over x times 10 x to the 9/10. When you divide two exponential terms, you subtract their exponents. So this gives us the limit as x goes to infinity of 1 over, actually it's 10 over x to the 1/10, because you do 1 minus 9/10. And when you plug infinity into this, it won't give you indeterminate because that 10's there. You're guaranteed to have a 10 on top. And then infinity to the 1/10. Infinity raised to any positive number gives you infinity. So infinity to any positive number is infinity. And so 10 over infinity gives you 0. So this answer is 0. This actually means something, because the fact that this limit gives you 0 means that this function is bigger than this function for huge values of x. We call that the order of magnitude. The order of magnitude of functions tells you as x goes to infinity which ones are the biggest. And as x goes to infinity, this function gets infinitely bigger than the log function. It takes a long time to do this. If you were to graph this function, log 3x is above the 10th root of x. And if you were to zoom out, you could zoom out for a long time, excuse me, and log 3x would still be on top. You have to zoom out to about 10 to the 15th. Once you get around those numbers, finally the 10th root of x passes log 3x. But as you go to infinity, not only does it pass log 3x, it gets infinitely above log 3x. That's the order of magnitude. The order of functions is this. Excuse me again. Log x is the smallest, then x raised to any real number, where n is a real number, then any exponential function, and then of course x to the x is bigger than all those. So that is the order of magnitude. This is how these functions line up as x goes to infinity. And all of this is proven with L'Hopital's rule. For example, if you wanted to prove that a to the x is bigger than x to the n for all real numbers n, you would just show that the limit as x goes to infinity of a to the x over x to the n is infinity. Because showing this is proof that the function on top is infinitely bigger than the one on bottom. And again, if it was like 2 to the x over x to the million, 1 times 10 to the 6. It would take a long time for 2 to the x to pass this function, like a long time. But infinity is incomprehensibly large. So infinity has all the time in the world. Eventually 2 to the x will pass it, and by a factor of infinity. So this is the order of functions. And to show why this is true, when you differentiate a to the x, it'll just give you log a times a to the x, which I think you proved that rule in one of your P sets. X to the n, no matter how big n is, when you keep differentiating it, eventually this n is either going to go to 0 or it's going to go to a negative number, at which case it's all this a to the x, because you differentiate a to the x and this always stays there. So L'Hopital's rule can be used to prove this order of magnitude of functions. But for us, it's almost like assumed. Like it's okay to just use the fact that that's the order to do math out quickly. So like if you had to do the limits as x approaches infinity of like log base 7 of x squared over 3x, well, this is a polynomial term that has a higher order. This thing goes to 0 because the one on bottom is bigger. But if it was 3 to the x, well, now that's an exponential term. Oh, it's still bigger. It still goes to 0. If it was 7 to the x squared on top over 3x, now you have the bigger function on top, the exponential function. This one goes to infinity. So it's a helpful thing to keep in mind, the order of magnitude.